This video presents the results of the research paper Distributed Spatial Multiplexing in MIMO Systems that was accepted for publication at 27th FRUCT conference. The authors, Mikhail, Bakulin, and Vitaly Kreyndelin, are coming from the Moscow Technical University of Communications and Informatics. Dmitry Petrov is with People's Friendship University of Russia, and Sergei Melnik is from the Central Scientific Research Institute of Communication. Firstly, I would like to introduce the topic and the problematics of the paper. One of the crucial directions in the development of wireless communication systems is the use of transmitters and receivers with many inputs and many outputs, so-called MIMO transmitters and receivers. MIMO channels significantly expand the capabilities of communication systems. However, the implementation of these capabilities requires appropriate algorithms for processing the transmitted information on both the transmitting and receiving sides. There are plenty of MIMO algorithms, and they help to achieve large performance gains. In particular, throughput grows almost linearly with the number of antennas. It is well known that optimal performance is achieved with the maximum likelihood receivers. However, they suffer from high computational load. Therefore, in practice, linear receivers are used, and VBLAST is one of first such receivers known already from 1990s. These receivers also have their problems. In particular, in linear receivers, the primary source of the MIMO channel is spent on suppressing interference from signals emitted by neighboring transmitting antennas. Therefore, the gain from diversity transmission and reception is lost. This leads to deterioration in energy efficiency. Next, about the problem, how this problem is tackled in our paper. We develop the signal construction approach for the MIMO channels, which provides additional gains from spatial diversity, even with linear receivers. So in the next few slides, I'm going to tell you about the system model that we are using, about the distributed spatial multiplexing MIMO transmitter and receiver, how we carry out the simulations, and what are the simulation results, and we'll draw the conclusions. Let us consider a mathematical model of a communication system with a MIMO channel and a spatial multiplexing. A simplified block diagram of such a communication system with spatial multiplexing is shown in the figure on the right side of the slide, on the top. Channel coefficients here are assumed to be constant over the transmission interval because we assume that propagation conditions are with slow frequency selective fading. In the left, you see the usual formulas how the signal is constructed and also the channel coefficients. These channel coefficients are Gaussian complex random variables with zero mean and unit dispersion. The coefficients can be independent or correlated depending on various factors, including the distance between the antenna, the number of scatterers in the environment, and so on. One may notice that in a conventional spatial multiplexing system, each symbol is emitted by one transmitting antenna. Therefore, it has only an R equivalent propagation path. And R is the number of receiving antennas, and T is the number of transmitting antennas. In order to increase the diversity gain, it is necessary to form a signal in such a way that each symbol X is emitted by each antenna. Therefore, the information contained in this symbol must be distributed across all the antennas. And a version of such communication system with the MIMO channel distributed spatial multiplexing is shown in another figure on this slide, also on the right, but in the bottom. The distribution of symbols over the antennas is carried out by orthogonal conversion, but also symbols are delayed by different values. Therefore, such a system can be called a delayed spatial multiplexing system. The signal generation model for the delayed spatial multiplexing system can be described by the expressions on the top right part of this slide. These expressions are state and observation equations of the Markov process. Therefore, a Kalman filter can be used as one of the simplest approaches for the evaluation of the vector of symbols Zn. In this case, the estimation algorithm will be described by the expressions that can be found on the bottom right part of the slide. It should be noted that the reception algorithm, like the well-known MSE algorithm, is linear. Therefore, to improve the quality of symbol detection, it can also be used as a part of the iterative algorithm with turbo processing. Turbo algorithm uses sequentially a Gaussian approximation, which is also linear. Then, the resulting estimates are refined by taking into account non-Gaussian distribution of QAM symbols. An increment of information at each step is used at the next step of iteration. The block diagram of such an iterative turbo receiver is shown in the figure on the right part of the slide. In order to validate the developed algorithms, the computer board was created in MATLAB and it's considered MIMO scheme with distributed spatial multiplexing. The simulations were carried out for a MIMO channel with 4 antenna configuration. LDPC channel code with a coding rate of 3 divided by 4 was used. In the figure on the right, you can find the frame error rate against the signal-to-noise ratio per bit for a system with conventional spatial multiplexing and distributed spatial multiplexing, usually in iterative turbo receiver. It's worth mentioning that if only one iteration of turbo receiver is used, then the reception algorithm becomes a conventional linear receiver. For traditional spatial multiplexing, it is MMSE, and for distributed, a Kalman filter. From the results, it can be concluded that the use of distributed spatial multiplexing gives us an additional energy gain of about 2 decibels. Moreover, this gain holds both for a simple non-iterative receiver and for a turbo receiver. Additionally, the use of iterative receiver allows us to obtain a gain of about 8 dBs with 3 iterations of the algorithm. Therefore, what was done in the paper? A new method of distributed spatial multiplexing for MIMO channel system is proposed. We simulate a transmitter where symbols after orthogonal transmission are sequentially emitted by each transmitting antenna. In the receiver, we can use either a linear Kalman filter or also together with efficient turbo iterative processing. And we are getting up to 2 energy gain with 1 iteration or up to 8 decibels gain or with 3 iterations of the algorithm. Thank you for your attention. Bye.